This video contains the solutions to the lines and curves in space practice problems worksheet. For this first question, we're asked for the equation for the line, and we're given a point that the line goes through and a vector that indicates the direction of the line. And that's all we need to figure out our equation. So our equation is going to look like r of t, and then in each component, we're going to start with the coordinate of the point that we're given, which is going to be -3, 2, -1. And then the vector that gives the direction, we're just going to add that as multiples of t. So plus 1t, plus 0t, and plus -2t. And then we can simplify this, so we get t minus 3, 2, and then -2t plus minus 1. So that is our equation. As we saw in the first problem, what we really want to easily find the equation for a line is a point and a vector that indicates the direction of the line. And we're not quite given that here. We're given a point, that's good, but we're not given the direction specifically. We're told that the line is parallel to the line 3 plus 4t, 5 minus t, and comma 6. And so if we can find the direction vector for this line, then that direction vector will be the same as the direction vector that we're looking for. So we can just sort of reverse engineer how this line was put together. We know that the multiples of t, that's where the direction vector comes from. So our direction vector is going to be 4, -1, and since we don't see a t in the z component, that just means that it's 6 plus 0t. So our direction vector that we're going to use here is 4, -1, 0. So the line that we're looking for, maybe we'll call this r2 of t, is going to start with the point that we're given, which is 1, and then -3, and then 4, and then add the multiples of t based on the vector that we're using. So 1 plus 4t, -3 plus -1t, and then 4 plus 0t. So we can write this in the normal way, 4t plus 1, -t minus 3, and then 4. And that will be the line that we have. For these next two problems, we're given two lines, and we're asked to figure out if the lines are parallel, intersecting, or skew. So parallel here would mean that they have parallel direction vectors. It doesn't have to be the exact same direction vectors, but if the direction vectors are parallel to each other, then the two lines will be parallel. So intersecting or skew would mean that the two direction vectors are not parallel. And then we can talk about what do we do, how do we figure out if they're intersecting or skew. But if they're parallel, then we're done and the two lines are parallel. If they're not parallel, then we'll have more to do. So what's the direction vector for R1 and the direction vector for R2? So again, just like we did in the previous problem, we're going to reverse engineer that direction vector simply by peeling it out of the way that the line was constructed. It's just the multiples of t. Same thing here, even though the parameter is called s, it's going to be the same thing, where we have -2, 3, -2. And what you might notice is that if I take that second direction vector and multiply it by -2, I get the first direction vector. And that means that these two direction vectors are, one's a scalar multiple of another, which means that they're parallel vectors. And that means that these two lines are parallel. And so we're done. If you're ever in a situation where you're not sure or you just don't see whether or not the two vectors are parallel, you can always take the cross product of the two vectors. And if the two vectors are parallel, then you'll get 0 when you take the cross product. All right, very similar problem here. So again, we're going to find the direction vectors, and if the direction vectors are parallel, then the two lines are parallel. And if they're not, then we'll have some more work to do. So the direction vector for R1 will be 2, 1, 7, and the direction vector for R2 will be -4, 1, -3. And it's easy to see that these two vectors are not parallel. For one to be a scalar multiple of another, there would have to be a scalar that I would multiply by each of the components to get each of the components of the other line. But the y component for both vectors is 1, so the only scalar that would work would be the scalar 1, which would mean the two vectors would be the same, and they're not. So the two directions are not parallel, so the two lines are not parallel. So now the question is, do the lines intersect or are they skew? So in order for the lines to intersect, there has to be some point on the line R1 and where that point is also on the line R2. In other words, there has to be some value of t and some value of s, where 4 plus 2t equals 12 minus 4s, and t, the y component of the R1 vector, equals negative 2 plus s, and negative 3 plus 7t equals 4 minus 3s. All three of those equations would all have to be true for the same value of t and the same value of s. And so this gives us a system of three equations with two unknowns. Now, this system might not have any solutions, but if it does have a solution, then that means that the two lines intersect at that solution. So let's just work through trying to solve this. The second equation here gives us a solution for t, so let's take that solution for t and actually substitute it into the first equation. That gives us 4 plus 2 times the quantity negative 2 plus s equals 12 minus 4s. That's 4 plus negative 4 plus 2s equals 12 minus 4s. So 2s equals 12 minus 4s, 6s equals 12, s equals 2. And since t equals negative 2 plus s, that would mean t equals 0. So it looks like there's a solution, but we haven't touched the third equation yet, so we need to make sure that that solution also works with the third equation. So let's plug in t equals 0 and s equals 2 and see what happens. When we do this, we get negative 3 on the left and negative 2 on the right. That doesn't work, and so that means that this system has no solution. This means that the lines don't intersect, which means that they are skew. So the solution here is that the lines are skew lines. If we had gotten a solution, then the lines would be intersecting, and the solution would tell us the point at which the two lines intersect. All right, last one here is a matching problem. So we've got 6 equations and 6 graphs, and we're trying to figure out which equation goes with which graph. And we're really just going to use a process of elimination here. So for example, graph E here is a line, and it's the only graph that represents a line. And if we look at our equations, the only one that is an equation, the only one that represents a line, is number 1. So E matches with graph number 1. Looking at Roman numeral 2, we see that Roman numeral 2 is the only remaining function that doesn't involve trig functions in some way. And so we would expect that everything that involves trig functions would have some kind of rotation or spinning or periodic sense to it. And so we're looking for a graph that doesn't have anything like that. And the only graph that doesn't have any spinning or periodicity is graph D. And so that's going to be Roman numeral 2. So we've checked up number 1 and number 2. Now when we look at number 3, we see that the z component is a constant 2. And that means that whatever this graph does, the z value will always be 2, will always be fixed. And if we look at our remaining graphs, the only one that only keeps a single z value for the entire curve is graph F. So that has to be Roman numeral 3. Now looking at Roman numeral 4, let's temporarily ignore the x component. Let's just put that aside for a second. We see that the y component is sine of t, and the z component is cosine of t. And we know that in the xy plane, if we have one coordinate being sine and the other coordinate being cosine, we will get a circle, we get rotation. And so we might imagine that this curve, this function here, the graph would have rotation in the yz plane. But then now if we look at the x component, which is 2t, that means the x coordinate is steadily increasing as t changes. So we see steady increase in the x direction and spinning in the y and z directions, and that's exactly what's happening in graph C. So the x is steadily increasing, and we spin around in the y and z directions. And so that's going to be graph number 4. If we skip down to graph number 6, we see a very similar setup, except if we temporarily ignore the y coordinate, we see that we're going to have spinning in the x and z direction and a steady increase in the y direction. And again, that's exactly what's happening in graph B. We see spinning around and then a steady increase in the y direction. So that's going to be graph number 6. And then by process of elimination, graph A has to be Roman numeral 5, and we're done.